Waves 5. Reflection. Okay, we've all experienced waves reflecting. If we've ever heard an echo, if we've ever seen a reflection in a mirror, it's everywhere. So we're just going to very quickly go through it. Not too much you need to know, and it's not too complicated. A little bit of terminology, that's all. So here we have a barrier that's going to reflect a wave. These are our incident waves. Now what we sometimes draw is we draw wave fronts. So this line would represent the wave, and all the points on this line are in phase. So let's say that's a crest, and this line here is the next crest. So the distance between those two lines is actually the wavelength, and that's just a convention that we do. And this is always drawn perpendicular to the direction of motion. So these are called the incident waves. They come in here and they intersect with the barrier. And let's draw some lines. What have we got here? Yeah. And so we have, this is perpendicular to the barrier, so that's 90 degrees, that's 90 degrees, and we would call this the angle of incidence, sometimes given a theta and an I, and this is the angle of reflection. Okay, and it's always measured from the normal. So this guy here is called the normal. So if we have a barrier like so, the normal is always at 90 degrees to it. Okay, another barrier over here, or interface, and the normal is always at 90 degrees to it. Let's try and remember that, because a lot of students want to measure this angle here, and it doesn't work because that's not how we've defined the angle of incidence and the angle of reflection. Alright, and here's our wavefronts. Now notice that when they hit here, the wavefronts have this distance between them, which is lambda, our wavelength, and that wavelength hasn't changed. Okay, and we can also say that the angle of incidence equals the angle of reflection. And there's our theta I equals theta R. And that's really all we need to know about reflection. Let's have a look at a couple of examples, and we'll demonstrate this in the class as well. Okay, now what we've got here is a picture of a ripple tank. A ripple tank is just a small pool of water, usually about that thick, that we make water waves in, and we shine a light through them, and where you've got a crest and a trough, you either get a beam of white light or a dark shadow, depending on what it's doing to the light. And we'll pull one out and demonstrate it to you in class. So here we have straight waves being reflected from a barrier in a ripple tank. So let's draw on this a little bit. There's our barrier, okay, and here's our wavefront coming in, okay, and they're coming in and they're a little bit lost here, but these are our reflected ones, and there's some here as well. Ripple tanks are notoriously difficult to see sometimes, so it's quite amazing that we've actually got this photo. And if we actually drew it, we would have that's our normal, okay, and our angle of incidence follows there. That would be, because that's 90 degrees, that's our angle of incidence. Let's change the color a little bit, and here is our, that will be our angle of reflection. Got that? Now it's a bit messy because we're not getting every reflection, but when we look at a ripple tank, you'll see this is pretty good for a ripple tank. Alright, so let's get rid of that, let's move on. So let's look at some different shape barriers. Don't have to be straight, they can be curved. And here we have our wavefronts coming in. This is the focus point for this curved barrier, and these are the incident waves, and so we would call these the reflected waves. And notice that we have straight lines in, but we get curved wave fronts out, and the curved waves condense and focus on that point and then go through, and we'll try and demonstrate this in class as well. Now, what sort of application uses this? Well, have you ever seen a satellite dish? That's exactly what a satellite dish or a microwave dish or any of the dishes that are used for communication do, because basically you get a wave front. Let's say you have a satellite dish for pay TV. This is coming from the satellite, and it's a fairly weak signal. So what happens is the satellite dish focuses all that energy into one point, and so you get a stronger signal just here. Works really well. Now, what happens if we, like on my pay TV at home, I have a two-way system. Not all satellite systems are like that, and so I can send data up to the satellite and talk to Foxtel or whoever they are. And so how does that work? Well, here you have a transmitter. It produces a wave which actually is a bit focused. Sometimes they go out in this direction as well, but we don't need to know that. It produces a round wave front. So these are our incident waves, and then our reflected waves are straight, and they head off straight off to the satellite, and so they're not being dissipated because they're a nice parallel wave form. Yep, and this is what we do in microwaves as well. If you look around the hills as you travel along highways, you often see microwave towers on top of high hills, and they're line of sight basically, and they talk to each other, send a lot of the internet goes through microwave communication networks. Okay, so that works as the reverse basically. Anything else we need to know about that? I don't think so. So now you should be able to do the chapter 14 questions 6, 7 and 8 in your workbook. Next video we'll look at refraction. See ya.